Hello, everyone. Welcome to this seminar. This is a Clever Planets series seminar given by Dr. Fabrice Gaillard. My name is Duncan Keller. I'm a postdoc with Sinti Lee and Raj Dasgupta here at Rice. Before we get started, I'd just like to say a few words on behalf of the Clever Planets collaboration. So Clever Planets is a multi-institutional interdisciplinary initiative to unravel the conditions of planetary habitability in our solar system and beyond. Its lead institution is Rice University, and it's supported by NASA as one of the teams for the Nexus for Exoplanetary System Science under the Network for Astrobiology. And we also have a land acknowledgement. Our research here at Rice University is pursued on the traditional lands of several native peoples, namely the Karankawas and the Sanas, as well as the Coahuiltecans, represented today by the Tap Pilam Coahuiltecan Nation, and the Ishaks, represented today by the Atakapa Ishak Nation. We see it as a duty to acknowledge this historical aspect of our identity and to foster a beneficial environment for all communities, in particular, those who preceded us on this land. Now about our speaker. Dr. Fabrice Gaillard is a director of research at the University of Orléans in France. In his own words, he is an experimentalist who specializes in high pressure and high temperature methods with a consolidated background in chemical thermodynamics. Dr. Gaillard's research covers a wide range of topics, from the physical properties of melts to magmatic systems of rocky planets and planetary habitability and surficial geochemistry, and much more. Dr. Gaillard holds the title of Habilitation à diriger des recherches, and last year he was honored with the European Association of Geochemistry's Ringwood Scientific Innovation Award. With that, Dr. Gaillard, please share your screen, and we are all looking forward to your talk.
Thank you, Duncan, for this introduction. I think it should be okay now. You should see the screen. Let me change the mode of presentation. And if I use the pointer, sorry. Okay. So now you should see my screen perfectly and the pointer moving. If you don't answer, I consider that it's okay.
Yeah, that's good.
So I'm going to talk about ATMOPHILE elements in Magma ocean. So this is a project that we are conducting in the framework of a collaborative project funded by the French Agency for Research. And the name of the project is Gaston. So Gaston is a famous comic in France, maybe not so popular in the US, but I will let Maxime explain you later who is Gaston exactly and what is funny in this sketch here. So ATMOPHILE elements, in fact, is also the elements that we call volatiles. Who are they? Mainly hydrogen, carbon, nitrogen, and sulfur. That's what I'm going to talk about today. We have also started to work on noble gases so that we can basically work on all these elements and compare their behavior with noble gas that are supposed to be just inert species that just passively goes to the fluid phase. Sorry. And on our to-do list is halogens. So the next elements on which we would like to work is those guys, indeed, halogens. So why do we work on that? It's because those elements are involved in the process that we call magmatic degassing. So what is magmatic degassing? It's in response to convection process in the Earth's mantle. Magma are produced and then they rise to the surface. And when they reach the superficial conditions, they release into the atmosphere a variety of chemical species. And these chemical species react in the atmosphere, controlling several important parameters, such as the temperature, the humidity, the redox conditions, or even the acidity of the surface waters. And as such, there is good reason to link the occurrence of life on a planetary system to this process of magmatic degassing. So magmatic degassing probably has an important planetary importance in that it can shape the chemical composition of the planetary suite. So I'm showing here the example of Earth and Venus. Those planets are really identical in terms of size and density. So let's broadly speaking about geophysical properties. They are the same one. The distance to the sun is very similar for both planets, but there is big difference. So Venus is dry, while the Earth is covered by water. The atmosphere is nitrogen rich, and there's a variety of biogeochemical cycles involving an oxygen rich atmosphere. But there is also similarities between both planets in that Venus, as I told you, is dry. It has an atmosphere composed mainly of CO2 and nitrogen. But if we calculate the mass of carbon in the atmosphere of Venus, we have exactly the same mass of carbon on the surface of our planet Earth. The difference is that on Earth, carbon is carbonates in sedimentary rock, mainly, while on Venus, this carbon is entirely partitioned into the atmosphere. And then there is also nitrogen, and then the mass of nitrogen in the atmosphere of Venus is very similar to the mass of nitrogen in the atmosphere of the Earth. So there is differences, but there is also similarities in the let's say the distribution of ATMOPHILE elements at the surface of the planets. And this probably tells us a lot about the process of magmatic degassing. So beyond Venus and Earth, there is of course Mars. We know Mars was once covered with some water, but nowadays the surface of Mars is relatively dry, and it's very rich in sulfur. We have a lot of sulfates covering the sedimentary sulfates covering the surface of the present-day Mars. And if we look even beyond Mars, we see here a small planetary body, which is a satellite of Jupiter. This is Io. And Io is a volcanically active planet. And you can see here on the top, I don't know if it's very easy to see, but we see something moving here. It's a plume. In fact, it's a volcanic plume, and there is volcanic activity on Io, very intensive volcanic activity. And what you see here is a plume of almost pure SO2, which is degassing from mafic, maybe ultramafic volcanoes on Io. So the question behind here is can we explain this sort of diversity of, let's say, superficial conditions to the diversity of magmatic degassing that we can find in the solar system? And if the answer is yes, so could we use this link to propose some sort of predictive model that would tell us what should be the atmosphere of exoplanetary system based on our knowledge of magmatic degassing? So I think it's possible, and this is what we have done in a 2014 paper. I'm a bit sorry for Raj because I came to Houston some years ago, and I already presented this slide, but I think it's good for the young people. We didn't see it. So what I'm doing here is a simulation, a numerical simulation of the process of magmatic degassing as a function of pressure. So pressure here is changed from 1000 bar, 100 MPa, and it goes down to 10 to the minus 6 bar. Okay, and in response to the depressurization of the magmatic systems, degassing occur, and this is what I simulate here. So the system I consider is a mob, say an ordinary mob. That's 80% of the volcanism of our planets. And I consider the volatile content in this mold, which you can read here. So it's what we usually find in molds. And then I have also to fix what we call the FO2. So that's the oxidation state of the system. And the value here is expressed relative to the firelight magnetite quartz buffer, more reduced than this buffer. So it's not really representative of mold, but it's representative of a sort of average oxygen fugacity in the solar system. So we see here three different panels. So let's start with the bottom panel, where you see the fraction of volatiles that is remaining dissolved in the melt. So you see CO2, H2O, and sulfur are at the highest conditions of pressure, all dissolved in the silicate melts. And in response to decompression, you see that first CO2, then H2O, and finally sulfur are released from the melt. So where do they go? Well, they simply go in the gas phase. The gas phase that you can see here on the right side on the picture, and this is the white smoke, if you want. So in this gas phase, you in fact find the species that are released by the silicate melt. And what you see is that at high pressure, the gas phase is mainly composed of carbon species, carbon monoxide and carbon dioxide. At intermediate pressure, let's say something around 1 bar, you see that the gas phase is dominated by H2O, which explains actually the white smoke that you see here on the picture on the right. And if degassing occurs at even lower pressure, let's say less than 10 to the minus 3 bar, which is very similar to what you have present day in the atmosphere of Mars, you see that sulfur species dominate the composition of the gas phase. On the very top diagram here, you have the detail of the speciation in the gas phase, and you see different species, carbon, hydrogen, and sulfur, are in different form. I don't want to comment that. This would be going too far into the details. But what you see basically is that for a given starting magmatic composition, a mob, if you degas this mob at high pressure, you would produce a dry gas which is dominated by carbon species, mainly CO2. In fact, you would degas a gas phase which has the composition of the atmosphere of Venus. Okay, and this is what occurs in a dense atmosphere, like the atmosphere of Venus, which is almost 100 bar of pressure. Now, if the same mob degas at 1 bar, let's say in the atmosphere of Earth, then it would release a wet gas, which would be dominated by water. And on the other side of the spectrum, at the very low pressure of degassing, let's say on Mars or Io, then the same mob would produce a gas phase which is dominated this time by sulfur species, and SO2 being the dominant phase. So you see that with this dependence on pressure, which is a really strong feature of the process of magmatic degassing, we can basically propose some very general, broad, predictive models that could link the process of magmatic degassing at the planetary scale and the physical and chemical status of the atmosphere. So please feel free to stop me at any time if you want to, if you have questions. So this is for the present day volcanism in the present day atmospheres of planetary suits. So what is becoming more and more interesting to discuss between specialists on these topics is, what about the time evolution? All these things, this magmatic degassing, atmosphere, magma, mantle convection, did evolve through time. In order to do so, we first need to, I mean, when I say did evolve to time, yeah, I mean, so let's go back deep in time, but this means also somehow let's go back deep in depth. So let's start with the sort of inventory of the volatile or atmophile element reservoir that we have, at least on Earth. On other planets, we don't really know. So on Earth, we have the surface. The surface is very volatile rich, or very rich in atmophile by definition. So we have the atmosphere, we have the ocean, and we have the crust. Now deeper, we have the mantle. And in fact, there is two types of mantle. There is the so-called depleted mantle, which is shallow. This is the source of Middleton-rich basalts. And this depleted mantle is depleted in incompatible elements. That's where the depletion terms come from. But it's also depleted in volatile species, mainly depleted in carbon and hydrogen. And then deeper, we have this mysterious enriched mantle. It's deep indeed. That's the source of oceanic island basalts. It's probably manifold, this enriched mantle, and it's probably a mix between primordial features and recycled features. And then there is the core. So the core, according to some recent papers that I think most of you have also read, the core might be probably the most important reservoir of atmophile element, which would be surprising, but it's probably indeed true. So there is many questions that people have in mind when they speak about this volatile reservoir. Is first, what is their size? What is the age of those reservoirs? And whether there was this famous secular evolution in that there would be exchange through the history of our planets between these different reservoirs. So a bit of drawing, there will be a series of drawing here. So what is this history? What could be this secular evolution? In fact, our planet has 4.5 gigayears of history involving outgassing and involving ingassing. So the outgassing is a two-step process. There is the primordial outgassing, which is the magma ocean, very early in the history of our planet, and the secondary degassing. And then there is so this secondary process of ingassing, which mainly involves subduction. So we did a review recently of all these processes. That was a very long and painful paper to write, more than 80 pages. I had the feeling I was rewriting a PhD. And then, but this was useful because we made it clear with this review that the two parameters which are really important if we want to understand the process of magmatic de and ingassing at planetary scale is these two parameters here, oxygen fugacity on the horizontal axis and pressure on the vertical axis. And so pressure means pressure of magma production, but it's also pressure of degassing. And basically, if you vary those numbers, you can generate a variety of chemical mixture. You can degas a variety of chemical mixture. And this is summarized here with this cartoon. And you see that, so there is just guesstimate here, there is no real calculation, but we have something relatively predictive in that we can link with this sort of conceptual picture, we can link the, let's say, the chemical status of the planetary interior, that is to say the oxygen fugacity of the mantle, to the mixture that this mantle outgassing would produce, and then the types of atmosphere that could be produced. Okay, and so why oxygen fugacity really matters for the behavior of those atmophile elements? It's expressed here with diagram where oxygen fugacity varies from very reducing conditions to oxidizing conditions. And so this is the very early magma ocean, let's say here on the left, and on the right hand side we have subduction zone, modern subduction zone volcanism. And if you look, for example, at carbon, you can see that it has a very different behavior depending on this parameter, this redox parameter. The same for hydrogen, and I think the strongest effect is for both nitrogen and sulfur, which are two anions dissolved in the magma. And because of this, they have a very special FO2 dependence. So basically, at very reduced conditions, those elements are not volatile at all. They only become volatile if conditions are oxidized enough. Okay. So what I propose to discuss now is those atmophile elements in the magma ocean, and they can be atmophile by definition, but they can also be lithophile. That's what we will see. And in certain conditions, they can be even siderophile. I don't think we will have the time to go through this during the talk. So I propose a twofold discussion. That's going to be, but I think we mainly have the time to focus on the first part, that is the degassing of the magma ocean via what I call gas silicate melts equilibria. So I will now present you a series of calculations. So in this calculation, I assume several things, but probably the most important one is that I consider that the volatile inventory that we have nowadays on Earth was present during the magma ocean stage. I'm talking here about the last magma ocean stage, and that is the one related to the moon forming impact. So assuming that the present day inventory of volatile elements on Earth were present during the magma ocean stage, I can then redistribute those elements between the magma ocean and the atmosphere. And if you want to see on the picture, so this atmophile element will be distributed between the magma ocean in orange and the atmosphere in blue. So in doing so, I define a sort of anchor point, a sort of starting point of the distribution of volatile elements that could be compared with the present day distribution of those elements that we have seen before. So of course, we have no rocks from this magma ocean that survive. There is no fossils of the magma ocean. So we have to go through simulations. These simulations are numerical, but they are based on experimental solubility laws that people have been calibrated since long. So I report here a series of papers that are used in this modeling. So many of the solubility laws that we are using are from my collaborators, but also I took you for example here the Armstrong work from Mark Ishman's group, and O'Neill and Mavrogenes for the sulfur. So I will now stress the recent work that we have done with Fabien Bernadou, who is doing a PhD with me. He will be finishing by the end of this year, actually. And then Fabien worked on nitrogen solubility in basaltic melts. And so he has done a couple of experiments which consist in equilibrating basalts with a fluid phase that is rich in nitrogen. So those experiments were conducted at relatively low pressure in comparison to what you guys are used to do in Houston. And that's because mainly we wanted to focus on really the solubility law that helps us to calculate the degassing process. So in terms of temperature, well, it's high, and in terms of FO2, we try to cover the very large range from very reduced to moderately reduced conditions. So here is the results of this paper. You can see here the nitrogen concentration in the silicate melts in ppm, which is equilibrated with nitrogen-rich fluid, which is plotted as a function of oxygen fugacity. So you see here a number of data points which reflects several studies. The studies of Fabien Bernadou correspond to the blue square here, and basically what you have here in sort of brownish pink colors correspond to 1 atmosphere data. Okay, 1 atmosphere data that shows two behavior, basically a behavior here at high oxygen fugacity, which is flat, so there is no dependence on FO2. And at lower FO2, you see a negative slope, which means that the more reduced you are and the more nitrogen dissolved in the magma. So the more nitrogen, the less volatile, if you want, is, or the less atmophile is nitrogen as you go more reduced. So the difference between those 1 atmosphere experiment and our experiment here in blue is just the effect of pressure. It's because we did our experiment at 800 bar and 3000 bar. So the solubility is a bit higher with increasing pressure. And we reported also some experimental studies from your group. This is the Grewal paper, I think 2019, yeah, which is obtained at even higher pressure, because here I think we selected only the data points at 1 GPa. So basically you have a trend which says 1 atmosphere, a couple of 100 bars, and 1 GPa. Okay. So these solubility law are only interesting if we can make a mathematical model of it, and then they can be used in a multi-component model of degassing, and this is what we have done. So we have proposed a solubility law for nitrogen in basalts. And in this solubility law, we can calculate the FO2 and the pressure dependence of nitrogen solubility. And importantly, we only need 2 species to describe the nitrogen solubility in silicate melts over this pressure and temperature range. So N2 at oxidizing conditions and N3 minus at low FO2. And this is important because in the recent literature, we have seen a lot of paper mentioning the possibility of NH3, or let's say NH something species that are dissolved in the silicate melts. And this is a very important implication if it's true. But for the moment, after this paper and with some more recent experiment that Fabien has been doing using double capsules to buffer the hydrogen fugacity, because this is indeed the cornerstone of this speciation issue. This is the hydrogen fugacity. And for the moment, we don't see any evidence of measurable NH species being dissolved in silicate melts. It doesn't mean that it does not exist, because there is spectroscopic evidence. People have been showing Raman spectra, and people from your group. But for the moment, I mean, as you know, Raman is not a quantitative tool, and it seems to us that NH species are negligible in terms of abundances and speciation in silicate melts, even under conditions where they could be very abundant. I mean, high hydrogen fugacity conditions, for example. Okay, so we have a solubility law for nitrogen that we can use and implement in a multi-component degassing model. So this is what we have done in a recent paper published this year. And you have here 2 figures where you see in the bottom panel the concentration of ATMOPHILE species in the magma ocean. And on the top diagram, you see the speciation of ATMOPHILE elements in the atmosphere. Here it's expressed in terms of atmospheric pressure in bar. And these 2 panels here use as horizontal axis the oxygen fugacity, which varies from very reduced to very to oxidized, let's say, like the present day mantle. So what do we see? Well, we see that both concentration of those ATMOPHILE elements in the magma ocean and speciation in the atmosphere vary a lot with oxygen fugacity. At very reduced conditions, we have CH4, for example, being present. 1%, it's quite a lot in terms of atmospheric properties and greenhouse effects and so on. And CO and H2 are the 2 components that would dominate, in fact, this atmosphere. Okay, so very reduced conditions, in fact, H2 would be the most abundant species. Then on the other side of the diagram, you have the oxidized conditions. And with oxidized conditions, what you see is that sulfur species would dominate in the atmosphere, would be almost the most abundant species after CO2. Interestingly, you see also nitrogen. Nitrogen, which is not volatile under reduced conditions, it remains dissolved in the magma ocean. And if conditions are slightly oxidizing, I mean, I'm talking about iron rustite -2, so it's not really oxidizing, but at those conditions, basically, nitrogen is almost entirely outgassed into the atmosphere. Okay, so oxygen fugacity really matters. But the thing is that we don't know what was the oxygen fugacity during the magma ocean stage. So from people studying core formation, we know that the magma ocean was very reduced, at least when the metal and the magma ocean did coexist. So it started from very reduced conditions, and that was the very early magma oceans. And as accretion proceeded, conditions became more and more oxidizing. And basically, when we look at the iron content in the Earth mantle, we deduce that the present day oxygen fugacity, we deduce that the last oxygen fugacity of equilibration between the magma ocean and the core was around iron rustite -2. So this defines, let's say, the low range of oxygen fugacity for the magma ocean. On the other side of the diagram, we have the recent Armstrong et al. Paper. That's the group from Bayreuth in Germany. And they suggested that, in fact, the magma ocean was very oxidized. The driving force for this high oxidation state is a process of disproportionation of iron that would be involved in the deep magma ocean at high pressure. And this disproportionation reaction introduced a lot of ferric iron in the upper magma ocean, causing very high oxygen fugacity at the surface of the magma ocean. So possibly very oxidized species degassed by the magma ocean on our planet. And more recently, there is the paper by Paolo Sossi and co-authors from ETH and IPGP, ETH in Zurich and IPGP in Paris. And they suggest, based on the ferric iron content of the present day upper mantle, they suggest that the magma ocean was in fact equilibrated at about iron rustite. And it was equilibrated with the atmosphere at this oxygen fugacity. So this figure shows you that oxygen fugacity is very important in defining what should be the composition of the atmosphere released by the magma ocean. But the problem is that we don't know what was the oxygen fugacity during the degassing of the magma ocean. Very reduced, very oxidized, or in between, we don't know. So with this slide, I discussed the speciation of atmophile elements in both the atmosphere and in the magma of the magma ocean. So now what I would like to discuss with you is to discuss numbers in terms of size. So switching from speciation to size of these volatile reservoirs that are the atmosphere and the magma ocean. So in order to do so, we need to assume a model. So either we melt the entire Earth, the entire silicate Earth, sorry, and then we make a global magma ocean, or a scenario which for several reasons I prefer, we consider that the magma ocean did not melt the entire silicate Earth and that there was a portion of the mantle that remained unmelted. And so the volatiles were therefore only involved between the magma ocean and the atmosphere, and this part of the mantle was untouched, if you want, by this process of degassing, or preserved by this process of degassing. And so the number that I use, I need to define the bulk abundances of these atmophile elements, and the numbers that I use are visible here on the screen. 90 ppm carbon, and those numbers for, let's say, the other elements, and this corresponds indeed to the present day This is the number you obtain if you sum the present day mass of carbon in the atmosphere plus the present day mass of carbon in the depleted mantle, and so on for all these elements. The surface plus the depleted mantle. These give you these numbers. Okay, so now from these numbers, we can calculate what is the size of the volatile reservoir formed by the process of degassing of the magma ocean. So let's start with the top diagram here. You have the mass of carbon, hydrogen, nitrogen, and sulfur in the atmosphere formed by degassing of the magma ocean. You see full lines, dashed and dotted lines, which corresponds to different size of the magma ocean. Oh, it's written here. Okay, different size of the magma ocean. We consider either 1/4 to 3/4 of the bulk sea at Earth that has been molten. So that's basically the depth of the magma ocean that is seen, that you can appreciate here with the different curves. So the depth has an effect, but it's not the strongest effect. Again, the most important effect is the effect of oxygen fugacity, which really control the mass transfer between the magma ocean and the atmosphere. So you see that indeed, under very reduced conditions, nitrogen remained in the magma ocean, and so there is almost no nitrogen in the atmosphere of the planets. And on the contrary, you see that hydrogen is very volatile under very reduced conditions, and because it's all H2. And on the contrary, under oxidizing conditions, hydrogen is not volatile anymore. Okay, the hydrogen remain dissolved in the magma ocean if conditions are oxidizing. And on the opposite, you see here sulfur. So sulfur is very volatile if conditions get oxidizing. Okay, so if you remember, I was mentioning the work by Armstrong and co-workers, proposing that the magma ocean was very oxidized at the surface, as oxidizing as the present-day mantle. So let's say hydrogen plus 4. Then if they are correct, the magma ocean should have emitted into the atmosphere a huge amount of sulfur. And basically there would be no more sulfur remaining in the magma ocean. Okay. So a very strong effect of oxygen fugacity on the size of the reservoir formed by the degassing of the magma ocean. Okay, so here are the numbers for the concentration of those atmophile elements dissolved in the magma ocean. So it's in the ppm range, and basically you see here, for example, that hydrogen concentration in the magma ocean are of the order of 100 to several hundred ppm in the oxidizing conditions, where basically there is no hydrogen release in the atmosphere. So we form in that case a dry atmosphere. All right. So now that we have these numbers, we have defined the size of the reservoir formed by the magma ocean degassing. We can compare that numbers to the present day reservoir. So let's talk first about the superficial reservoir. You see here the mass of hydrogen, carbon, sulfur, and nitrogen at the surface of our planets, expressed in gram. And you can compare these numbers with the different curve that we see here. And it's really shocking. I really mean it. It's really shocking that the mass of nitrogen that is present at the surface of our planet nowadays is almost identical to the mass of nitrogen that should have been degassed by the magma ocean 4.5 billion years ago. And we could almost say the same thing for carbon. Carbon is here in gray, and you compare that with the carbon content in the modern Earth on the surface, and you got almost identical numbers. Those two elements behave as if nothing happened for them since 4.5 billion years ago. So subduction, in-gassing, even secondary outgassing doesn't seem to have changed to those numbers, or there is a compensation effect, maybe a compensation effect that imply that those numbers remain stable, although there was outgassing and there was ingassing. Why not? But this is not the case for hydrogen, for example. Hydrogen, this is the present day mass of hydrogen at the surface of our blue planet. And you see that in most cases, hydrogen is not released by the magma ocean. So there is a big difference between the atmosphere, the hydrogen content in the atmosphere of the magma ocean and the hydrogen content at the present day surface of our planet. Maybe if conditions were very reduced, hydrogen could have been released, but in that case, nitrogen would not be released. So we just displaced the problem. So this is what I wanted to say for the superficial reservoir. Now we can compare the concentration of atmophile element in the magma ocean with the concentration of those same elements in the modern depleted mantle. You see here the dots for sulfur, carbon, hydrogen, and nitrogen. And what you can see again, it's not so different. It's not so different. If you look at the nitrogen content in the depleted mantle, see the range 0.1, 0.3 ppm. Well, it's about similar to what is expected to remain in the magma ocean if degassing, let's say, occur at oxygen toxicity higher than iron vesite -2. For the carbon, again, you see here the range of carbon content that it can have in the magma ocean. It's not that different from the range, which is, by the way, very heterogeneous, of carbon content in the modern depleted mantle. And we should not be surprised by this, because we have already discussed the behavior of hydrogen for during degassing. So this is the hydrogen content in the modern depleted mantle. And according to the calculation, there should be much more, there was much more hydrogen dissolved in the magma ocean than the content of hydrogen in the present day depleted mantle. For sulfur, that's about right. In fact, sulfur, if it's not degassing as it is supposed to do during for most of the FO2 conditions we can see here. So then we have the magma ocean would contain a massive concentration of sulfur that is comparable to the depleted mantle. Okay, so now last point of comparison with this diagram. You remember at the beginning of the talk I was saying that Venus and Earth are very similar in terms of geophysical properties. But I was also saying that the mass of carbon and nitrogen at the surface of Venus and at the surface of planet Earth are very similar. Just that the speciation is changing, but otherwise the mass are very similar. And this is indeed what you can see here. So here the big smiley here represent the mass of carbon at the surface of Venus. And it's really identical to the mass of carbon at the surface of our planets. And here is nitrogen. Okay, so maybe what this is telling us is that the present day abundance of carbon and nitrogen on our planets and on planet Venus was fixed by the magma ocean stage, and since then, for some reason, it did not change much. Okay, in one slide, degassing of the magma ocean is controlled by oxygen fugacity. So we can consider two cases, and I only show you the first cases, which is melting of the depleted mantle, and we can discuss later if you want the second case, which is melting of the bulk silicate earth, but the result won't change much. And also we see that the size of the magma ocean finally does not have such a strong effect. Then the conclusion that we reach at this stage is that the outgassed mass of nitrogen and carbon by the magma ocean are similar to the present day superficial reservoir for these two elements. So, and this is very surprising. And similarly, the concentration of those elements in the magma ocean are very similar to the concentration of those elements in the present day depleted mantle. The things are more complicated for hydrogen and sulfur because of their FO2 dependence, which are opposite. And there is really an issue here with hydrogen, which is not volatile. It's only volatile at very reduced conditions. And this is really, I think, a major issue for our understanding of how planet Earth evolved blue as we know it. It's because if we can't find a way to outgas hydrogen from the magma ocean, in fact, it can hardly be outgassed via volcanic degassing, simply because of the very first slide I show you. That is that H2O is not really volatile if degassing occurs in a dense atmosphere, like the atmosphere we expect for the magma ocean. Something like a few, almost 100 bar. If we degas the magma in this atmosphere, it will not release its water. So if we don't release the water from the beginning, that is during the magma ocean stage, it sounds like we are running into a sort of runaway process where water will never be able to outgas from either the magma ocean, so the primary outgassing events, or from the secondary outgassing events, that is volcanism. So if we start with a dry magma ocean atmosphere, I'm afraid we remain dry forever, and that's probably what happened to Venus. Just to finish, we are working on the publication of a paper that explains the degassing code that we have been using for this paper. There's going to be a computer and geoscience paper, but for the moment we have set up a web application where people could use our code to calculate basically the simulate all the things I've been showing to you today. So the input are the temperature, the size of the planets and the magma ocean and so on, and then you enter here the number we are mostly interested in, that is oxygen to gaseity and the concentration of the different volatile species, and this should return you the composition of the atmosphere and the abundance of the different volatile species in the silicate melts, and this all in the silicate melts, and it can even tell you if graphite saturation occur at the surface of this planet. Okay, so thank you very much for your attention, and I hope I've not been too long.
Thanks, Fabrice.
Yeah, we can take some questions. Thank you, Fabrice. I guess, Raj, it looks like you have a question, so why don't you go ahead?
Hi, Fabrice. Yeah, one thing, just a clarification, maybe I missed it. So in the Barnardou et al., the nitrogen solubility model from last year in chemical geology, did you mention that the speciation change from N2 to N3 minus in the melt that's happening around IW, is that correct?
Yeah, yeah, it depends on pressure, but yeah, that's about, I might show again the slide.
Yeah, so that's what I was going to, so from the plot, looks like there is a pretty big pressure dependence. So yeah, meaning that transition is shifting to much lower FO2 as you go to higher pressure. Is that something the model fit required, or the data actually showed it speciation wise?
Well, the data, there is not enough data to be able to see that. I try to put back the presentation, but it doesn't want to share again. I try to reshare, but and in fact the pressure dependence is because I did not stop my. Do you see the screen?
I see the last screen now.
Yeah,
if you go back.
I can't go back. In fact, it's completely blocked.
Okay.
Fabrice, you may have to mouse over in the bottom left. There might be a little left arrow button that will show up if you hover your mouse on the PowerPoint. Sometimes that's what happens for me.
So I try to close many.
When it's in the full screen mode.
No, I'll restart. Okay, I'll restart. I will be able to show the slide. Here it is. Do you see the? No, you don't see because I don't share my screen. Sorry. Now you should be able to see it.
Yeah, I see it.
Yeah. Okay. So indeed, the model require it. And you see that there is a shift as pressure increase. The shift from N2 speciation to N3 goes toward more reduced conditions. So at atmospheric pressure, it's about R_-1 -1, and then at high pressure, this is just 1 GPa actually. It reaches R_-5, and this is in fact required by the stoichiometry of the reaction and their pressure dependence. I don't have the written the reaction here, but if you write the reaction, yeah, you see that there is so this is N2 produce N2, and here this is N2 produce 2 N3 minus. So there is a square root relationships with the hydrogen pressure with the nitrogen pressure for the N3 minus species. And so this implies that if you increase in pressure, but this is the N2 pressure, okay? So if you increase the N2 pressure, indeed you do expect a shift of the transition from N3 minus to N2, and this is just a stoichiometric effect. Now, does the data show it? It's relatively clear to me that it's not the case now. No, we do not have. Well, actually, I mean, look here. Here you see a slope, and here you see a slope that is not that strong. So we might still be in sort of a flat region. Maybe they show it, but in order to confirm it, we would need data here, you know, at very reduced conditions and high pressure.
We have a question in the chat from Pratik Chowdhury, which I'll just read here. Nice talk, Fabrice. Does Io having an SO2-rich atmosphere mean that it was oxidized during the magma ocean stage, or has it oxidized later in its history? Any ideas on why Io has such an SO2-rich atmosphere?
Well, Io, so maybe I was not very clear. So Io currently is an active planet in terms of volcanic activity. It's a very active planet. It's not a planet, sorry, but it's a very active planetary body, and it does produce indeed volcanic plumes that are almost pure SO2. But there is almost no atmosphere on Io because the gravity on Io is not strong enough to retain this atmosphere. And just next to Io there is Jupiter, which is huge and has a huge gravity. So it probably captures, you know, the atmosphere of Io. So there is a very low pressure atmosphere, let's say, on Io, if we can call that an atmosphere. But the surface is very sulfur rich, indeed. Now the question is, does SO2 degassing require oxidizing conditions? I mean, I modify a bit your question, but this is what it means. In fact, SO2 degassing becomes something very important if pressure is very low. And here, in that case, you see that the oxygen frequency is not that high. You know, it's FMQ minus 1.4. So MOBs, you know, they are at FMQ. So they are almost 300 times more oxidized, or richer in oxygen, if you want. So the simulation is done for a very reduced case, and the thing is that at low pressure, SO2 is really favored by the just because of the it's again a story of stoichiometry of the reaction, which imply that at low pressure you can make a lot of SO2, and for the same magmatic system, if you look at the speciation of sulfur at high pressure, you see that you have H2S, for example, that becomes important. It can be important. And as pressure decreases, H2S is less and less important, and the same for S2 is less and less important, and SO2 is favored. So SO2 does not mean necessarily that there is oxidizing conditions in the interior of IO. And in fact, the degassing of SO2 is telling us the opposite. It's telling us that the process of degassing and releasing of SO2 reduce the magma. Let me explain. In fact, the sulfur in the magma initially is present as S2 minus. This is an anion, and this is the reduced form of Venus. This is the reduced form of sulfur. And if you degas SO2 from such sulfide, let's say, bearing magma, it means that you remove oxygen from the magma in order to degas as SO2, and quite a lot actually. This is 2 O2 for 1 S that you degas. So this is really consuming a lot of oxygen. And so the fact that IO does release a lot of SO2 in the atmosphere, in fact, it means that it's reducing the interior of the planet. So SO2 does not necessarily mean oxidizing conditions, and SO2 degassing does reduce the system, in fact.
Maxime?
Yeah, great work, really interesting. I had a question about, while we're on this slide, about actually this effect of pressure. And I was wondering what was the rationale for this. Well, I'm aware that's not really the main topic of this talk, but that's something. So can I kind of envision this pressure dependence on water outgassing as if I'm, for instance, just thinking of a Henry law? Is that because the exponent in the Henry law would be different from 1, or, well, that's not the reason for it to be, but that's how it can be interpreted.
No, the driving force for this pressure dependence of the speciation is the volume change, in fact. It's just because when you write the reaction between H2S and SO2, there is you increase the number of mole. So I mean, we need to write down the reaction, and in fact I think there is 3 mole on the right hand side of the reaction and 2 moles on the left hand side. So there is a volume change if you assume ideal gases. There is an imbalance in terms of mole during the speciation change from SO2 to H2S. And so the high number of moles is on the SO2 side. So this means that if you depressurize the system, you move to the SO2 side. Okay, just because of the volume change.
Okay, I see. And is that a similar reason for water? For the influence of pressure on water outgassing?
You mean
that's increasing the pressure suppresses.
This is driven really by the solubility law.
Okay, so in this case, that would be because of the Henry law exponent.
Henry law, exactly.
Yeah. Okay.
Yeah, in that case, it's because water is soluble much more than SO2, than CO2. Okay, so in fact, if the pressure is high enough, all the water is dissolved in the magma, and CO2 is not soluble enough, and then it's released in the atmosphere. Okay.
Okay, I see.
And in that case, indeed, that's a sort of Arian law. Even if the Arian law is not valid for water, it's a square root relationship.
Yeah. Okay, and so I guess then, well, I guess we kind of touching upon that, but I was thinking about what you kind of concluded the talk with, that if there is this thick CO2 atmosphere, at the end of the magma ocean phase, then there's no chance you outgas the water that is contained in the mantle. And I was trying to imagine how that would occur, because in order to have a drawdown of that CO2 and to form, I guess, carbonate or whatever it is, then you need water, right? So that's
you need water. So if you don't have water, then you don't have carbonates, and so the CO2 remains in the atmosphere, and so you don't degas water.
I see.
But you don't degas. You prevent somehow massive degassing of water, which would otherwise occur if the atmosphere pressure is low.
Okay.
I mean, it's not completely dry. I think you can see it. I know I don't have the slide here. Okay, but it's not completely dry. You always have a bit of water anyway in the system. You see, even if it's a lot here, but still, you could have 0.1. 0.1 is 10%. Okay, so 10%. If you have 40 bar, for example, you would produce a gas that contains 10% water. It's not a lot, but it's not zero. But if it's 100 bar, then it's very difficult to release water.
Yeah, okay. I guess that would be interesting here to see whether you could condense this water at, well, that's for 1300. Okay, but upon cooling this atmosphere, maybe at some point you could still condense a bit of water.
Yeah. I don't know if some people have tried to do that actually. I remember that there was a guy in the NASA who was talking about that, trying to simulate the simultaneous degassing and sort of condensation of water, with trying to identify some bifurcation, let's say, in some case where the system would become drier and drier and drier, and the other case the system would be wetter and wetter. But I'm not seeing any papers for that story.
Do you remember the name?
No.
Okay. Well, if it comes back to you by Friday, I would be interested.
Yeah, I think it's a NASA guy, but I forgot who it was.
I have a quick question. I really enjoyed the talk, Fabrice. Thank you. I'm a mineralogist, and I like to think about things from that perspective. And you mentioned in the talk that, of course, there are no rocks left from the magma ocean time. I saw on the sketch that you showed on several slides with the magma ocean that you had graphite and diamond participating, or at least present in some of these processes. And I recognize that this is a provocative question, but if somehow there were to be diamonds preserved from these processes in the first, say, 100 million years of Earth's history or something like that, would we be able to recognize them by the inclusion suites or some, maybe the nitrogen substitution or some process that we would be able to identify in something we found in a kimberlite on the modern Earth, do you think?
That's a very interesting question. I have no idea. Well, they would be very old.
Obviously, statistically, I think the odds are very low. But if there ever were to be a piece of physical mineralogical evidence of these processes, I think that's probably what it would be, right?
So, I mean, maybe we could eliminate. We could probably not identify magma ocean diamond, but we could eliminate, because we know that otherwise the two recipes for producing diamonds in the mantle is from carbonatite smells or from CH4 fluids. I don't see, I mean, maybe Raj knows better the topic than I do. I think these are the two ways of producing diamonds in a modern.
Certainly, anything with a recycled isotopic signature would be eliminated.
So we know how to identify those types of diamonds. I think it's basically based also on nitrogen isotopes, and so we know how to recognize these two types of diamond. And if you find diamonds that are not from in which we cannot recognize either the carbonatite signature or the CH4 signature, then it could be a magma ocean diamond. Otherwise, It's a very good point. I think there is a project that starts. I think it's led by this is an ERC proposal, an ERC project. So those are the prestigious European grants, and this is an Italian guy from Padova who got it. And I think he wants to search for the very primitive diamonds with his project. So I don't know how he will look at that, but you might find the answer in the summary of this project, which you can find on the web. This is a guy from Padova. He got an ERC grant on diamonds and primary diamonds and so on.
Yeah, I mean, there's been some astounding discoveries of things like ringwoodite in diamonds and ice polymorphs in diamonds that obviously are coming from sort of transition zone depths. So maybe if there's a primordial mantle reservoir that participated in the magma ocean in some way, but hasn't been thoroughly remixed, and somehow that's sampled by upwellings that get kimberlites. It struck me when I saw the diamonds in this cartoon. I thought, oh, I wonder if we'll ever see that.
What actually so you see I draw some small arrows here that shows that diamonds in the magma ocean would in fact sink, and that graphite in the magma ocean would in fact float. And in fact, the neutral buoyancy for diamond in the magma ocean, if it makes sense in a convective magma ocean, but it's another question. But the neutral buoyancy should be close to the transition zone, to the present day transition zone. So if the mantle was diamond saturated, if the magma ocean was diamond saturated, then if something is preserved from this, looking in the transition zone would not be completely crazy.
Interesting. Thank you. Well, if there are no other questions, we can thank our speaker, and please stay tuned for the talk that's coming 2 weeks from now for the next entry in this series.
Thanks, Fabrice.
Thank you, guys. Bye-bye. Take care.
Bye.
Thanks, bye.